morning's final speaker is Ellis Yuan. He's going to start talking about scattering equations and QFT amplitudes. Please join me in welcoming the speaker.
I'm very pleased to be invited here to give two lectures. It's my first time being in Taiwan. So in this lecture, I'm going to do a very pedagogical introduction to scattering amplitudes and how to use them to construct scattering amplitudes. Here I decided I would like to have the title of scattering questions and QFT amplitudes. In particular, by working on the QFT here, I would like to insist that this formulation that I'm going to introduce you is quite general in several senses. First of all, we don't really care about what kind of how many space-time dimensions we have. And also, we don't quite care what kind of theory we are studying. Or maybe I could say. Here, the object that we are studying, first of all, let me fix the context. We are looking at the Minkowski background. And also, we are just looking at the product theory test matrix. So we are considering elements in this predictive test matrix. For the most part of my talk, I'll just focus on tree level, which is relatively well studied. And this will be most of the talks I'll give you today. And tomorrow, I plan to talk a little bit about the developments over the past year. And perhaps I'll finally land on some comments about the one story and one loop in the end. But today the talk is very basic. And also by the QFT, I would also like to draw your attention to the talk by Oliver. Who's going to do an introduction to the amplitudes in superstring theory. And actually, if you compare the two, you'll find many amusing similarities, which should be more. It's surely worth to be investigated more. So let me begin. Yesterday, I got an idea that this time perhaps I would like to introduce the scattering equations in a little bit different setup. So at this point of the program, I guess most of you have got already familiar with the remarkable formula found by Taylor in the context of n equals 4 super Young Mills. Actually, this is not quite, it doesn't quite matter because we are only considering gluon scattering at tree level. And here, we are looking at the configuration of MHV, where we have, say, n particle scattering, but then we only have two particles which have negative helicity, and all the others have positive helicities. And here I'm looking at the partial amplitudes after the color decomposition, which Yuan has introduced in the first day. And so this formula in general looks like this. It's very simple and compact. First of all, we have a factor in the numerator that takes care of the helicity. And then in the denominator, we have something very symmetric, which goes from 1 to 3, which is inner product, all the way to n1. And the denominator is very cyclic symmetric. And you may appreciate this remarkable formula very much if you have ever suffered from the tedious calculation from Yuan diagrams. So usually when this such simplistic happens, it really indicates there should be something remarkable or deeper, largely kind, that we should understand better. And here I'm going denominator, and think about whether I could do something that can be generalized to more general situations, but not only restricted to NHV. So what I would like to consider is that I want to replace each of the inner product by something which looks like the form of some variables that I introduced, which I call sigma. Let me use sigma A minus sigma B. Temporarily, I haven't assigned a meaning to them. It's just a simple formal replacement. And you may wonder why. If you are not familiar with the string theory or any analog, you may feel this is very abrupt. But actually here I'm going to tell you this is actually not. But to let you appreciate why I do this, let's go back to review a little bit about many interesting relations that people have loved a lot over the years in Yuan scattering. They fall into several types. So you already know that if we are studying the 4 Yuan amplitude, we can do color optimization. And especially the summation is over all the permutations modulo the cyclic ones. And then summing over the trace of the color structure, and then the partial amplitude, corresponding partial amplitude, which are labeled by a certain letter ordering, which here I denote as alpha. This alpha belongs to this permutation. So here, in general, after this decomposition, we have altogether n minus 5 factorial of them. But people have already known very well that actually this is redundant. And to make computation efficient, we can actually reduce the number of objects that we have to compute. And it turns out that we can reduce this partial amplitudes all the way to the calculation of only n minus 3 factorial of them. So what kind of relation are we using to do this further reduction? The first one that is very well known is the so-called Yuan decoupling identity. And it has a form that you can first pick up one label to be unique, which here let me choose n. And I'm considering an n particle scatter. And you can sum over n minus 1 partial amplitudes where you insert this label n in every possible place. So this label A sums from 1 to n minus 1. This should be 0. And physically, this means that if you are considering the column group of UN, the U1 inside should decouple from the rest. And if you compute corresponding contribution, that means the whole summation should be 0. Another one, which is also well known, is the so-called Weiss-Querieff relation, which is sort of generalization of the U1 decoupling identity, which asserts that if you have this partial amplitude, and if I write the label as 1, then some alpha, then I put the label n as some sequence of label beta. Here alpha and beta denotes some sequence of labels. Then it can be expressed as a summation over kind of sequence gamma, which belongs to a certain permutation, which can be temporarily used in this notation. Then we can, for each of these gamma, we can put a corresponding partial amplitude, which whose labeling looks like 1 gamma and n. We put the n all the way to the end. And this is again an identity among the Yang-Mills amplitudes. And this notation denotes the set of all sequences then from the denominator, we get a very natural object, which we can define as object C that depends on an ordering. Maybe let me be more explicit. Here in particular, I have the ordering 1 to n. And that is defined by 1 over sigma 1 to sigma 2, 3, all the way up to sigma n1, where by sigma ab, I denote as sigma a minus sigma b. But this is an object that we can extract by this from this replacement. But now we can try to see what happens if we replace every Young's amplitude by the corresponding object we have obtained from this replacement. And then if you do it in your computer, you can immediately find that the relation, this identity automatically holds just algebraically. You don't have to assume anything about the sigma variables. It's plainly true. So somehow these two relations are trivialized by this object. But if you are dealing with Feynman diagrams, it takes a lot of work to prove them. Then there's a third set of relation, which is very remarkable, which is due to Yuan Kraskov and Johansson. Yes, it's in where the last two speakers are among the audience. So they look at the structure, detailed structure of tunable Young's amplitude, and by doing that, they discover a remarkable relation among, again, among the Young's amplitude, which is independent of this. In a form that will be suitable for this talk, we can write it like this. So we sum over a label A from 1 to n minus 1. Then we put an S of n A. So here by this n A, I mean the euro minus that variable, kn plus AA. Then we also put the summation over B from A to n minus 1. Then we sum the, again, the Young's partial amplitude, where we put the labels like 1 up to A, then N, here it should be B. A plus 1, and all the way up to N minus 1. This is again 0. Now we can try to see whether we play the same game to substitute the Young's amplitude by the corresponding factor we get. What may happen? First of all, you can, for each label, for each A, you can first have a look at what this combination should be. And after some computation, it turns out that the latter part becomes something like a C with label 1 to up to n minus 1. The label n doesn't enter inside. But then in the end, you get another factor, which is like 1 over sigma A minus sigma n plus 1 over sigma n minus sigma 1. Now, this factor and this factor is universal. And so we can first of all pull this all the way out. It doesn't care. And then if we first look at the second term, this summation is just a momentum conservation, which means that this guy is just there. And then what is that? As a consequence, we found a summation over A from 1 to n minus 1, then we sum over ns of na over sigma n minus sigma a, which is 0. So just by playing this simple game, we discovered this equation, which the sigma variables are supposed to satisfy if we insist that the relation has to hold. Of course, here I'm just pick up some particular label n, but in principle we can pick up all or in other words, we can try to integrate over all the different configurations of the sigma variables that we have introduced. Then, in order to build some object that may be some analog of the amplitude, we also need to take care of these equations which have to hold. So naturally, we can also insert these equations as some constraints. So here, let me introduce some notation. Denote each of the equations by f of the corresponding label. And so I can insert these equations into this integration. And then, in the end, I just need to put some arbitrary functions which can be determined later. And I can claim that this is some object that I would like to call A, as long as I can make sense of the integration. Now, here's a very interesting claim. So since we are integrating over all the configurations, it's very natural to expect that this whole part should be invariant under permutation of the labels. And in particular, in this case, since I'm going to use this C object that I wrote here, I can write part of the remaining stuff as the C of the corresponding label. Say, if I'm going to construct something for the Yuan mules, and for simplicity, let me use the canonical ordering that I've been using. So here, correspondingly, I'm putting C up to N. And then there could also be something remaining. And let me temporarily denote it as I of R, which I'll explain later. But temporarily, let me make this assumption that this I of R, the remaining part of the integrand, also satisfies this condition. It is fully commutation invariant. Then we could see that if we use this whole object in any of these relations, then according to the property that the C object satisfies, these relations are the direct consequence of this formula. And so this is a part of the motivation that why we would like to consider such an integral representation for the amplitudes. But in order to make everything precise, I still haven't told you how to precisely define this part, which I call as the measure. And let me also denote it as d mu of the corresponding number of particles. So in order to find a way to define this measure, let's look at the properties of these equations a little bit. First of all, we can think about some transformation on the variables. So for each sigma variable, let's try to do an SO2C transformation on it, which sends it to something like an alpha sigma plus beta, gamma sigma plus delta, where the coefficient, this parameter satisfies the determinant of this guy equals to 1, and they are complex valued. So under such a transformation, every combination of the form sigma A minus sigma B, if you do the computation, you can find that it transforms covariantly. It turns into sigma A minus sigma B over gamma sigma A plus delta times gamma sigma B plus delta. Then there is something interesting happening to the equations. So now if we use this knowledge to look at, to study how the equations should behave, you will find that each of the equations also behaves covariantly. Yes, first of all, the corresponding vector for for the A is universal, so we can put it in front. But then there's another factor inside. But then we can plus the sigma A and minus a sigma P right here to do some manipulation. And then it turns out that this equation, this expression becomes this. In here, I'm just in it as the original equation. But then there's something like gamma times gamma sigma A plus delta. Then sum over the different from A, and then only the S of AB. But then this is another momentum conservation. So this drops out, and then it turns out the equation also becomes converged. So that means that this set of equations are really properly defined as a function of some coordinates on a Riemann sphere, because due to the fact that the equations, this F expressions behaves covariantly. So the proper way to treat these variables that we have introduced is to regard them as a set of coordinates which belongs to Cn, but then we have to modulo the SL to C transformation. An equivalent, you can consider a Riemann sphere, and each variable can denote the location of a puncture on the sphere. And so on. And also, obviously from the equation, we don't like to consider the configuration where the sigmas pinch. So effectively, that means although we have n sigmas, there are really only n minus 3 of them which is independent. But then you may wonder whether the equations, since we have n of them, they are over-constraining the sigma, so in general we won't have any solutions. But it turns out not, because you can consider the combination of summation over all the labels and address each of the equation by corresponding sigma A to some power. And this will always be automatically be 0 if n, this power equals 0 or 1 or 2. When it equals 0, this is purely cancellation of different terms from different f's. And then if it's at 1 or 2, you also need to use momentum conservation. But then as long as the corresponding S final states are really data from a on-shell scattering process, this always holds. And so that also means altogether there are only n minus 3 independent equations. And so everything looks fine. So how can we precisely make sense of the integration that we are doing? Given this fact, it's actually very easy. So for the D and sigma part, we basically just need to replace it by some certain combination. First of all, we can pick out any of the 3 labels. Let me denote them as A prime, B prime, C prime. And I can put a factor of sigma A prime, B prime, sigma B prime, C prime, sigma C prime, A prime, and then put all the remaining matter, where this A is different from A prime, B prime, C prime. And we can choose arbitrary values for the sigma A prime, sigma B prime, and sigma C prime. And that's it, how we fix the gauge fixing. then for the constraint part, we can do something very similar. Again, we can pick out some arbitrary 3 labels, which can be different from these 3. And then correspondingly, we put a similar prefactor. And then basically put the product of all the remaining stuff. And in combination, again, according to the previous notation, I'm calling this whole part as d mu n. And so in general, we have this expression. Okay.